I welcome you all in this lecture on system model of electromechanical system, and this lecture is part of our course on modeling and simulation of dynamic system. So, today basically we will be looking at the electromechanical system, and as the name indicates that it is going to be a combination of electrical system and mechanical system. Okay. So, we will be seeing that how can we combine the two systems, electrical and mechanical system. Some combination of this we have already seen in case of bond graph modeling, where we combined these systems, okay, with the help of power bonds, and here we will be seeing that how can we derive the system equations for electromechanical system. So, these devices, electromechanical devices are such as say potentiometer, motors and generator, and they transform the electrical signals into say rotational or translational motion and vice versa. Okay. So, this is what they do. The potentiometer, for example, it could be a rotary potentiometer or it could be a linear potentiometer, and it has input of rotation or linear motion and output of a potential difference. So, here also we have the mechanical and electrical system being combined. Then if we take example of say an electric motor, it has input of potential difference and output of rotation of the shaft. So, that is there, and of course, a generator which is reverse of electric motor, it has got rotation of the shaft as input and output as the potential difference. Okay. So, here in this lecture I will be discussing about the first two examples here. Of course, there are many more examples which you can refer through some of the standard textbooks. Okay. So, first let us take the case of potentiometer. Now, we know that potentiometer is used for measurement of say rotation or translation. Okay. These devices are very much useful in say low cost motor, low cost servo motors, okay, where we want to measure the rotation of the motor of the shaft. Okay. So, there these devices are used say mostly in the robotic applications. Okay. So, here I will be just talking about a linear potentiometer. The potentiometer, as I said, it is a displacement measuring device, and it is a variable resistance device whose output resistance changes as wiper connected to moving objects moves across a resistive surface. So, here you can see that as this wiper moves across this resistive surface, the resistance changes, and based on this linear motion of this, we get the electrical signal, okay, or we get the voltage here. So, in this figure you can see that say Vi is the input voltage and Vo which is not written here, Vo is the output voltage, and say R1 and R2 are the variable resistances, okay, and say RL is the internal resistance of the voltmeter, which we usually take to be of very high value. Now, we can calibrate this potentiometer as follows. Say when x is 0, when this x is 0, R1 is our maximum because this pointer will be at this position. So, our R1 will be R maximum, and at that position R2 is going to be 0. Similarly, when x is x maximum, that is this pointer is at this place, your R2 is going to be R maximum and R1 is going to be 0. Okay, this one is going to be 0 because this x is going to be the at the maximum position. So, this type of thing mathematically we can express these two conditions using this relationship. R1 is equal to 1 minus x by x max into R max, and R2 is equal to x by x max into R max. So, you see here, when you are going to put x is equal to 0, you are going to get R2 is equal to 0, that is this condition, as well as when you are going to put x is equal to 0 here, you are going to get R1 is equal to R max. Okay. Similarly, here when you are going to put x is equal to x max here, you are going to get R2 is equal to R max, and when you are going to put R2 is equal yes, and at that condition, when you are putting x is equal to x max, this term will be 0. So, your R1 will be 0. So, basically with the help of these two equations, we can calibrate the potentiometer. Now, here you see that this voltage is Vi, and of course, the voltage here is going to be Vo, output voltage. So, if I apply the Kirchhoff's law here, so this Vi minus Vo is going to be the IR1. Okay, IR1 here, and so I can find out the value of I from here, that is Vi minus Vo upon R1. Okay. Now, if we take RL, that is the resistance of the voltmeter at very high, as I said in the beginning itself, I can write V output Vo as I into R2, or I can substitute for this I, and this is going to be equal to Vi minus Vo upon R1 into R2. Okay. Or what I do here, I write Vo into R1 by R2 is equal to Vi minus Vo, that is this and this, I simplify this and these terms here. Okay. And from here you can see that I can write expression, I can basically take this to the left hand side, and I can write expression for Vo as R2 by R1 plus R2 into Vi. Okay. And this R2 R1 plus R2 is the maximum value of the resistance. Okay. So, R1 plus R2 I just write here as R max. So, this is R2 by R max into Vi, and we have already seen that R2 by R max, R2 by R max here is basically x by x max. Okay. So, I can substitute this value in my this result. So, I get Vo is equal to x by x max into Vi. Okay. So, this is my output voltage, and this is equal to x by x max into Vi. Okay. So, now depending on the value of x, okay, I will be getting the output voltage. Okay. And this is how the potentiometer works. Okay. So, basically the linear motion x is getting converted into the output voltage Vo. Okay. And x max, of course, I know the distance maximum up to which my pointer can move to the extreme value. So, this value is known, this value is also known, and for given this value I will be getting an proportional voltage. Okay. So, this is what is this is how we can explain the potentiometer. Fine. Now, if your potentiometer is a rotary potentiometer, as I told you, which are used in the say low cost servo motors, okay, there these rotary potentiometers are used. So, here there instead of this x, we are going to have the rotary coordinates, that is the theta. Okay. So, VO is equal to theta by theta max into VI. So, this is how the rotary potentiometer can be explained, or for the rotary potentiometer, the angular rotation of the potentiometer is can be measured in terms of the voltage. Okay. Next example I would like to take that of the DC motor. Okay. So, here as all of know, in mechatronic system electric motors are often used as actuators. Okay. So, you take example of any mechatronic system, whether it is your say photocopier machine or any robots or say washing machines or any mechatronic systems, motors are used as the actuators. Okay. And they are mostly used in position or speed control systems. Okay. The basic principle of motor can be explained, of course, all of you have studied in your school as well this basic principle, that is a current carrying conductor, when it is placed in a magnetic field, there is a force on the conductor. Okay. So, a force is exerted on a current carrying conductor placed in a magnetic field. This is what we also call it as the Lorentz law. Okay. And this force called Lorentz force is given as F is equal to BIAL. Okay. And this direction can be given by basically your right hand rule. Okay. So, through right hand rule you can for a given direction of the current and field, you can find out where the force is going to act. Okay. So, this magnitude of force is BIA into L, okay, where the B is the magnetic field strength, IA is the current through the conductor, and L is the length of the conductor. Okay. So, this is the expression for the Lorentz force, which is developed in a current carrying conductor in a magnetic field. There is another law which is used in the modeling of motors, and that is what is called as the Faraday's law. Okay. It states that when a conductor moves in a magnetic field, then an electromotive force EMF in short is induced across it. Okay. And the induced EMF is equal to rate at which the magnetic flux sweeps through the conductor. Okay. Swept through by the conductor changes, or in short what we say that E is equal to d phi by dt. Okay. And this minus sign, as you know, which comes from the Lenz law, which basically means that its direction is such that okay, or its direction is such that it opposes the cause generating it. Okay. Or the negative sign is because this EMF direction is such as to oppose the change producing it. Okay. That is, the direction of induced EMF is such that it produces a current, and this current sets off a magnetic field which tends to neutralize the change in magnetic flux linked to the coil, okay, and which was responsible for the EMF. And this induced potential is also called, what we call it as the back EMF. Okay. So, if say I take example of say let us say a magnetic field is created by a permanent magnet here, the north pole and south pole of the magnet, and here is the current carrying conductor is placed. Okay. Now, the Lorentz force, from Lorentz force law we can find out the force if of course there are n such wires here, and that will be just multiplication by n of the force which was generated in a single conductor. Okay. So, it is n times BIAL, and if this width of this conductor is say B, we are going to have a torque, and that torque is equal to F into B. Okay. Because here you can see that this force and this force they are opposite in direction. Okay. So, and the length between these is B, and they are going to turn your conductor. So, that torque is F into B, where B is the width of the coil. Okay. And thus this torque will be basically becoming NBIAL into B. Now, if you look at this expression, you can see that this torque is proportional to BIA. Of course, N is fixed, the number of conductor coils are fixed here, L is fixed, B is fixed. Okay, because these are the length parameters and these are the number of coils. So, basically this torque is proportional to B and IA. Okay, where the B is the magnetic field and IA is the current through conductor. Okay. So, we can put these NLB as some constant, say K1, and the remaining two things I can just write at BIA. Okay. Now, using the Faraday's law, the second law which we have seen here, the first law we have seen as the Lorentz law, which is responsible for the Lorentz force, and the second law, from the second law we can see that the back EMF is proportional to the rate of rotation of the armature, that is omega, and the flux linked to the coil, that is B. Okay. So, this VB is written as some constant into B into omega. Okay. Here this K2 is a constant. Now, as I said, so your torque is going to be a function of B and IA. Okay. So, based on what you are going to change, okay, you can have the torque. You can get the torque both way by say keeping IA constant and varying B, or by varying IA and keeping B constant. So, let us see the DC motor with armature and field coil separately excited. Okay. So, this figure shows you say the DC motor, this is the armature, okay, and on this armature you have the armature conductor, okay, through which the armature current passes. Okay. And here we have the field poles, okay, and of course here the field coils are there, and these field coils are responsible for the generation of the magnetic field, okay, B. So, here I can just draw a schematic for this motor here. So, the field coil, as I was telling you, we have a field circuit say here, and say the voltage supplied to the field coil is Vf, okay, current through the field coil is IF, and of course here we have the field coil has got a certain inductance say LF, and it has got a certain resistance say RF. Okay. And this shows the schematic for the armature circuit. Okay. So, the armature conductor which are here, these conductor will have certain inductance say LA, basically the A subscript is used here for the armature and the F subscript is used for the field. Okay. So, these conductors have the inductance LA and they have the resistance RA, and say a current IA is passing through them and a voltage of VA is supplied across the armature terminals. Okay. And you have the back EMF being which is being generated, that is say VB, fine. And after this you have the mechanical element. So, you have a shaft here and at the end of the shaft say you have got a load, alright, and this load that is an environment is there, say there is a bearing here, okay, and that bearing is generating certain bearing reaction, okay. Say that bearing torque we can approximate by considering a damping behavior. So, we can take that as equal to some damping constant into the rotation of the shaft, okay. So, that I will be telling you. So, now as I was telling you that the torque generated by motor is function of two things, the B and IA, okay. So, let us see first one, the armature controlled motor. Now, in this type of motor field current IF is held constant, okay. So, we are keeping this IF as fixed, okay, and the motor is controlled by adjusting armature voltage VA, okay. So, a constant IF means that the constant B. So, as I said, in armature controlled motors we are keeping the B as constant, okay. So, when you take B as constant, if you want to vary torque you need to vary the IA, that is the armature current, fine. So, here the back EMF VB will be equal to K2 times B omega, or as I said, since B is constant I can give it some other constant name K3 into omega, okay. So, this is armature controlled motors. Now, using Kirchhoff's law here for the armature circuit, I can write the VA minus VB is equal to say LA DIA by dt plus IA RA, okay. So, this is the VB is the back EMF and this is the voltage applied, alright. So, this will be the net voltage and this is going to be equal to LA DIA by dt plus IA RA, okay. Now, here you see VA is known to us, or this is the one which we are going to apply, okay, and VB we have just found out as K3 into omega, assuming B as constant, okay. So, here this is K3 omega and this is LA DIA by dt plus IA RA, okay. The current IA in the armature generates a torque, okay. Since for an armature controlled motor B is constant, as I have been telling you, in armature controlled motor since we assume that the IF is constant, so my B is constant, okay. So, sorry. So, since B is constant I can write T as K1B IA, I can take this B also as a constant. So, this is basically the K4 IA and this torque is going to be the input for my load system, okay. So, if we neglect the torsional effect of the shaft, of course, if you want we can model that also, but let us make the problem simpler. I neglect the torsional effect of the shaft. If I represent RB as the bearing resistance, then the net torque acting on the load is T minus RB into omega. Here basically this RB replaces the C, the damping coefficient, which I have shown in the previous schematic figure, okay. So, the net torque acting on the load is T minus RB omega, and I can substitute for this T, that is K4 IA minus RB into omega, okay, and this net torque will be responsible for the angular acceleration of the load, okay. So, this net torque I can write I d omega by dt, okay, because this net torque is going to be responsible for the angular acceleration of the load. Okay. So, the relation for armature control motor could be this one. So, this is basically our what you can say that combination of electrical and mechanical terms here, and here also combination of electrical and mechanical terms. Okay. So, here you can see that this omega is basically the rotation of the shaft. Okay. So, of course, from here we get the back EMF. Okay. So, VA minus this is equal to LA DIA by DT plus IARA, and this is of course the equation for the load. Okay. That is the inertial force is equal to your the torque of the motor minus your whatever the torque because of the bearings, okay, or the damping torque, whatever you want to say. Okay. And from here as I was telling you, we are more interested in knowing the relationship between the input VA and the output omega. So, from here if I can eliminate, substitute IA from here to this equation, then I can get an equation in terms of VA and omega. But you can see that these equations are in terms of derivative. So, the best way of doing that would be that we take the Laplace transform and convert these differential equations into the algebraic equation and get a relationship between the omega and VA. That we can always do, and that I am not dealing, I am leaving that as an exercise to you. Okay. Now, let us see the okay. Before we proceed further, I just wanted to show you the power of bond graph, and if I represent that is the motor equations, both these equations can be represented, okay, or these equations are modeled automatically using this bond graph model. Okay. Here you can see this is the armature portion here, the inductance of the armature, the resistance of armature, and this is the voltage supplied. At this end you are getting the back EMF. Okay. So, this is VB, the back EMF here, and that of course is equal to K4 into omega as per the gyrator relationship. Okay. And here of course you have the load, and here you have the bearing resistance. Okay. So, if you are able to draw this model, this bond graph, you will automatically get those two system equations, one which I have shown in the previous slide. Next, let us move to the field control motor. Okay. So, the previous case there we assumed the IF, that is field current, to be constant. Okay. Now, in this type of motor armature current is held constant. Okay. So, basically armature current is held constant in this type of that is field control motor, and this motor is controlled by varying the field voltage. Okay. So, here you can see for the field circuit, again using Kirchhoff's law, I can write Vf is equal to that is the total supplied voltage, Vf is equal to IfRf plus Lf dIf by dt. Okay. And what the field current leads to production of a magnetic field, thus a torque acts on the coil, and this torque is given by K1 BIA. Okay. Now, you see that here, since we are going to change the B, okay, because why we are going to change the B? Because here I am changing the current. I am going to control it by the varying the field voltage. Okay. Armature current is held constant here. So, here my B is changing and armature current IA is held constant. So, what I can do is that this K1 IA I can make it a constant into B. So, I give some name to it K1 IA, say some K5 into B, since I am assuming the armature current to be constant here. Okay. Now, this again this B is a function of IF. Okay. So, more the IF, more the B you are going to have. So, I replace this B with IF. So, this torque is K5 into IF. Now, once we have got the torque expression, if I neglect the torsional effect of the shaft, the net torque I can write as T minus RBW, where RB is again the bearing resistance. Okay. So, that RBW if I subtract from the T, I will have the net torque, and this net torque is going to be responsible for the acceleration of the shaft. Okay. So, this is I d omega by dt is equal to T minus RB omega, or I can substitute for this T as K5 IF minus RB omega. Thus, the behavior of the field current motor can be described as these two equations. Okay. That is Vf is equal to IfRf plus Lf dIf by dt. This equation basically we wrote for the field circuit, field coil circuit, and this equation is basically that is the inertial force inertial torque here, and that is equal to the torque generated minus this is the what you can say that the bearing force or the damping force or the reaction torque here. Okay, because of the bearing. Alright. So, the output here you can see that it is omega and the input is Vf. So, again if I want to have a relationship between omega and Vf, okay, what we can do is that again we can take the Laplace transform and convert this differential equation into an algebraic equation and get a relationship. Okay. So, these are the references. If you want to further read it, one is our book that is Intelligent Mechatronic System, and you can refer the W. Bolton Mechatronics from Pearson Education. Thank you.